Let's move to B part 7, tensor algebra for physics and classical mechanics, and also for electromagnetism. Now, lecture 1, formal definition of 0S tensor at P belongs to the manifold. In the context of intrinsic geometry, geometry defined independently of any embedding space, a tensor of type 0S at the point P belong to the manifold is defined as a multilinear map on the tangent space using only a structure, in this case internal structure. This is to the manifold M. Let's give a precise definition of a tensor 0S tensor at a point P that belongs to the manifold. And also this P over here belongs to the chart, and the chart is construct, okay, and the manifold. Points on the chart are points belong to the manifold. They are just label. So there is no dot product. You see, that's important here. And a tensor of this type at P belongs to the, this is a tangent vector space. It is a multilinear map. TP, you see, this here belongs to the tangent vector space. You see, that is a multilinear map. S-linear. Multilinear is the same of S-linear map, such that tensor T at P, which is invariant, those here are the components, okay, the contravariant components, which belongs to the tangent vector space. And this over here is the basis. Basis vector also belongs to the tangent vector space. Now, TP is a multilinear over R, that is a linear in each argument, as you will see in the application. Each input is a tangent vector in TPM, the tangent space, tangent vector space. The output is a real, attention, tensor is a map, you see? Tensor is a map. This leads to the real number, you see? Now, let's continue here. The tensor depends only on the point P that belongs to the manifold, not on nearby points belong to the chart, okay? Or coordinates. That's important here. I'm concentrating, my focus is the point P that belongs to the manifold. Coordinate representation. You see, this here, these are coordinate representation, okay, using this here as a basis vector, okay? This basis vector belongs to the tangent vector space, which are, in this case, covariant. But the amplitude, okay, these belongs to the tangent vector space, but this belongs to the, it's called contravariant because this is upper indices. In this case, the coordinate representation in a local coordinate chart, U, X, I, P belongs to the chart, then these are the components, you see? Attention, these are covariant components. Covariant component because you have here lower indices. So this belongs to the cotangent vector space. These are the basis vector, okay? Which also belong to the cotangent vector space. Or, in this case, I can denote this, you see, this tensor product symbol, okay, that S linear, which is multilinear map. This is T asterisk is a tensor product. This belongs to the cotangent vector space. This is important to emphasize that I sub I is dummy index because I1, you see I1 here, I1 over there, I2, I2, and IS and IS, you see, they are, in this case, scalar, okay, because they are dummy index. Then I can denote, as we did over here, you see this notation, then we can write, okay, denote as this tensor product S linear map, tensor product space. You see, the components of Ti1 to Is are values of the tensor when applied to the basis vector on this here. There's a basis vector that belongs to the cotangent vector space. You see, cotangent vector space. That's called dual space. That's it. I will continue, okay, next lecture to obtain the components, okay, of a tensor. That's will be our next lecture. See, that's what I will do, okay, in the next video. See.